So we determined one of the equations, which is the equation for the radial velocity. Let's now determine the equation for the tangential velocity. The tangential velocity with respect to the local standard of rest. Now let's determine that from the Oort diagram. Let's clear up the lines that we draw. So the tangential velocity with respect to the local standard of rest, this is the total velocity, and this is the radial velocity. Then the tangential velocity would be along this line. And again, you can also decompose the velocity of the local standard of rest into a component along the line of sight, a tangential component. Therefore, the tangential velocity is going to be the velocity of the star, capital theta, times sine of alpha, now minus the velocity of the standard local standard of rest times the cosine of the galactic longitude. And once again, we need to eliminate the unmeasurable angle alpha. Now again, from trigonometry, we can say that this side here, the opposite side to R naught in this triangle, in the whole triangle here, which is equal to R naught times cosine of L, it's also equal to the distance d from the sun to the star, plus this distance, which is the distance from the star to the center of the galaxy, times sine of alpha. So we can write R naught cosine L is equal to d plus R sine alpha. Now, isolating alpha in this equation, we find sine alpha, and substituting that in the equation for the tangential velocity, we find this equation. Now let's group together the terms containing cosine of L, and finally substitute this by omega, the omega r's. What you have with that is Oort's second equation. Now this equation permits you to compute omega in terms of the observables tangential velocity, cosine of galactic longitude, and the distance, and the known values for omega naught and R naught. Again, if you have a rigid body rotation, this product here, omega minus omega naught, cancels, and then you would only have omega d as a tangential velocity, as you expect from rigid body rotation.